Way back when we wrote down our list of axioms for vector spaces, you might have nitpicked with this list a little bit. For example, it says that we are required to have an additive identity, but there's nothing that says that the additive identity has to be the only additive identity. For all we know, it might be possible for there to be two different additive identities. So you might have wanted to add to this list that our additive identity is unique. Similarly, you might have wanted to insist that our additive inverses are unique. But this list of properties is actually carefully tuned so that things like that, we actually get them for free from the list of axioms we already have. So let's have a look at the uniqueness of our additive identity, in other words 0, and additive inverses. So for our additive identity, let's assume that we have two additive identities. So let's call them maybe V and W. So V and W are additive identities. I should say at the very beginning we're fixing some vector space, capital V. Okay, so we have a fixed vector space in mind. Suppose it has two additive identities. Is that even possible? Well, since this is a general vector space V, the only thing we know about it is that it satisfies the axioms of vector spaces. But there are a lot of axioms for vector spaces, so that gives us some stuff to work with. In particular, we can know for sure that this vector V, that is one of our additive identities, it has to be equal to V plus W. And the reason that this has to be true is because W is an additive identity, right? What being an additive identity means is that when you add it to something, it doesn't change, right? So V has to be equal to V plus W. But, you know, V is also an additive identity. So that means V plus W has to be equal to W. So you see that we thought we had two additive identities, but this shows they're actually the same thing. So we didn't need to assume that we had a unique additive identity. We actually can show that we have an additive identity just using the axioms of vector spaces that we already wrote down. A similar thing happens for additive inverses. So let's take some vector v in capital V, and let's suppose that U and W are both additive inverses for V. Remember what that means. Being an additive inverse means that if you add V to your additive inverse, what you get is the 0 vector. And here I'll actually write 0 because we've shown that it's unique. So there's no ambiguity if I write 0. In fact, maybe I'll put a vector hat on it so we remember it's a vector. All right. Also, U is an additive identity for V, so we can say for sure that V plus U is equal to the 0 vector. Okay. Well, remember, all we have available to us is the axioms of vector spaces. What we're kind of hoping is that if we have two different additive identities, or sorry, additive inverses, they're actually the same. So, right, what we're kind of hoping in our minds is that actually U is equal to W. So let's see, could we show that? Well, let's start with U, and then hopefully at the end of a big calculation we'll have W. Well, we can produce, really the only option we have is to say that U is equal to U plus 0. And that's true because 0 is the additive identity. But right, we need to get V's and W's in the game somehow, and this equation lets us do that. We know that 0 is equal to V plus W, so we can write U plus 0 is V plus W. Incidentally, I'm not writing parentheses to indicate the order of what these operations are, because vector addition is associative. That means it doesn't matter what the order is, so I don't need to write the parentheses. Okay. But now, look, we have u plus v. U plus v is equal to 0, so this is 0 plus w. But 0 plus w, 0 is an additive identity, so that's 0. That's w. So we thought maybe we could have two different additive identity or additive inverses, but this shows that in fact no. You can only additive inverses are unique. There's only one additive inverse for any given vector little v. There are a few other properties like this that you might want to add to the list of vector space axioms, but actually follow from the axioms that we already have. For example, you might suspect that the additive inverse for v is -1, the scalar -1, scalar product with the vector v. And that is something that you can show using the axioms we already have. I'll let you do it as an exercise.